So what I wanted to make sure we had a chance to cover, and great talk by Gavin, because I think it's actually very related in a lot of ways. As we look at this sort of world of industrial work, how are robotics, drones, artificial intelligence all playing a key impact to really understanding the future of industrial work. So a lot of my talk today is going to be about autonomy. In our case, it happens to be drone autonomy, which we've been focused on for the last 4.5 years. The application of artificial intelligence, particularly off sensor-based networks and sensor-based data, and how that is really impacting industrial use cases. So Kespry's been really focused on this idea that like industrial work can be changed in mining locations and construction locations, flying drones over rooftops to understand volumetrics and dimensional analysis and damage that's occurred on a roof, all for the case of just improving the way that industrial work is accomplished. If we look at the background of how this has all emerged, it's interesting to juxtapose some of the things that we already heard in the first prezo and a little bit of where I'm kind of synthesizing it upward into what I really think of as really what's happening with a lot of these robotics, drones, and just sensor-based networks that have emerged. For us today, the use of drones, which now has been populated to over 250 customers, several hundred drones that are now flying mostly in North America, but as much as 40,000 plus missions that we've completed in the last several years. It's because of the fact that the data that's generated, particularly on sensors that are coming off the drone, are becoming incredibly valuable to almost have a very realistic understanding of what's happening in physical space, and then being able to synthetically generate the data necessary to model and simulate what's effectively happening in physical space and digitizing it. And so a lot of the focus and attention for Kespry now is not so much on does the drone fly, because we've gotten sort of well past that point in terms of the hardware, and I'll talk to you through what we've done for the last several years on that front, but really about taking sensor-based information and starting to fuse that together into synthetic models of physical assets. And so when you think about these synthetic models that we're effectively building, one of the first ones that we got started with, does anyone know what this is, by the way? What's that? It's a mining pit, yeah. So it turns out that mining pits are some of the hardest, most difficult places for work to be accomplished because, as you can probably see, this material is being stockpiled up, right? Does anyone know how you get inventory tracking and measurement in a mining pit as a kind of status quo of the way that market works? It's weight, right? So what you're looking at here is a belt, conveyor belt that literally takes the material off of a stockpile, crushes it, and measures the weight as it's being crushed. Okay, so that's one way, right? So weight base. Any other methods for being able to understand how much material we have here? Yeah, so there's aerial surveys of volume, which is where we advanced forward a lot of techniques, and I'll show you some examples of this. But the one in between, it turns out, is taking a stick, a GPS stick, or a backpack, climbing the stockpile itself, taking 20, 30 points of measurement, and basically extrapolating what the rest of that material looks like. The challenge is that the moment that you put it on a belt scale, or the moment that you have a GPS stick or a backpack doing your measurements for you, what ends up happening is you have very few data points that's really involved to create the volumetric calculations, and effectively you have variances of what's actually the real material versus what you measured by as much as 20%, right? So this is kind of the way this world works, and this was our first use case. Because what we ended up doing in the mining aggregates world is we took aerial imagery, in this case, the fact that a drone is now flying about 200 feet above a key asset area. And what we started to do is we took imagery in a way where we can actually take angles around that imagery and basically construct a photogrammetry pipeline. And what that means is that you can take 2D images, stitch them together to create very accurate three-dimensional models. Turns out we went from 5 customers to 150 customers in a year just on that use case alone. So what that looks like today is pretty interesting. So I'll just do a quick demo of that. I'll switch back and forth between demos as we go through this talk. So this is one particular use case, and what you're looking at here is, I believe, the 5th largest coal plant in the world. It's somewhere, I think where is this? Wyoming. Okay, so we're in Wyoming, and we're looking at the Jim Bridger coal plant. What you're seeing here is not imagery that's taken from the drone, but a fully constructed 3-dimensional model, a 3-dimensional orthomosaic that's layered on top of 2D satellite imagery. And the way you can tell the difference between drones and the 3-dimensional model and the satellite imagery is this precise border right here, right? Because you can literally see the tire tracks, you can see blurry images. The reason that becomes interesting is not because I'm just going to show you a number of pretty pictures, but we can now synthetically model what the height and dimensionality is. We can now start to layer in a contour of how much elevation is involved with this specific area. It's not a 2D model, as I mentioned earlier, it's a 3D model, so we can now generate a fully realized synthetic digital twin of that entire space. To give you kind of perspective on this, this is about 3 football fields in length and about 50 feet high, right? So to do this kind of measurement with a stick, right, you're talking about weeks of work that would be involved, and it's inaccurate. So suddenly, you can now start to do this kind of volumetric assessment with a drone and get accuracy within 1% of forecast variance with a drone flying overhead within a single hour of drone flight. And interestingly, to the point that was made earlier, many consumer drones only fly for about 20 minutes. A lot of where our time went early on in terms of creating a fully autonomous drone solution for industrial work is that we actually got the battery times extended for our drones to about 35 minutes, which is a massive difference, right, in terms of just being able to maintain flight and being able to compose a model like this. So we can go capture this kind of data, 150 acres of coverage within about 30 minutes of flight. So a fair degree of ability on a single flight, and then the mission planning in Kespry is built in a way that the drone flies back to the location where it started from, a battery can be swapped out, and you can do mission continuation. So what's compelling about this particular use case is that it's not just the fact that we have a 3-dimensional view in imagery and a 3D model, but I can actually now do all kinds of volumetric calculations from that same concept. So what I'm starting to do here is effectively draw a polygon directly around the asset. And so the idea here is that as I bound this polygon, I will be able to immediately calculate how much area is effectively involved. So one of the next steps that we're actually taking is, instead of me manually bounding the polygon, we're actually now using deep learning algorithms to identify what a stockpile of material looks like and continue to kind of recognize what a specific stockpile looks like in comparison to other stockpiles and be able to train that effectively. But in this case, I'll just go ahead and put a little marker in FirstMark. And what you're seeing here is we've automatically calculated the area. At 64,000 square meters of area in this particular stockpile. I want to then go ahead and understand what the volume is. So what I'm basically going to do is, if this was the flat surface, I'm going to put a few base points down to create a base plane and then volumetrically calculate everything that's above the base plane. So I have to do this with, 2 hands on one. So I'm just dropping several base points down here so that my volume can be calculated. It's the only part of the demo where I just couldn't go with 2 hands, but thank you. No, I'm good, Matt. And we'll go ahead and put the density of coal, which happens to be 0.75 kilograms per cubic meter, and save it. And so basically the Kespry cloud at this point is going to go ahead and calculate what the cut volume is, the fill volume, and the mass associated with that particular stockpile. In this case, we now have a cut volume of 659,000 cubic meters. I added the density in, and of course that then calculates out my mass of 494,000 kilograms of coal in this particular case. That is hyper accurate within 1% of the actual material that was there. Complete game changer in the mining aggregate space, because now you have a way of being able to conduct industrial work measuring things like volumetric stockpiles without having the danger of someone climbing that stockpile, getting hurt, spraining a leg, breaking an arm, the usual things that tend to occur in these markets. The second thing that we started to think through is, let me just get out of my full screen here, is how this then gets applied from a artificial intelligence and machine learning standpoint. So we started to realize that a lot of the streaming sensor-based information that's being generated from these sources can actually then be automated in terms of, what the size and volumetric of a stockpile is. In the case of one of the next examples that we started to get into in the insurance and roofing sector was not only dimensionalizing the actual size and dimensionality of a roof, but how could we actually look at damage assessment? And how could we use convolutional neural networks and other similar deep learning models to identify what damage looks like on a roof? In this case, we started to apply this for hail damage, for wind damage, for weather damage, specifically on a roof. And so we ended up with these outcomes, where the bounding boxes that you're now seeing here are now accurately understanding what hail damage looks like after a major weather event with a 90% accuracy of what is hail and what isn't hail. Humans at this point can understand hail damage at an 80% accuracy. They're also climbing the roof, falling off the roof. It's the third most occupationally hazardous job in the country. And now we're able to enable that same industrial worker to be able to accomplish the same amount of work with a level of productivity that's unprecedented. So this one got a lot of attention because of the superstorms, particularly Harvey and Irma this past year. We were selected by farmers to effectively become the company of record to do this kind of work. The farmer CEO got up on air and said that the use of drones, particularly for claims adjudication, is now driving the industrial worker, in this case being the roof assessor, to be able to cover 3 homes per hour versus 3 homes per day. So quite literally a 10x productivity improvement because of the way that this kind of work can be accomplished. Same idea, you can even see it in the demo, where instead of us looking at a volumetric measurement of a stockpile of material, in this case, we'll look at a roof. We'll see that we can automate all the dimensional calculations directly on a roof. Again, this is not a 2D model, this is a 3D orthomosaic. So as I go into the details, you'll see that there are all these little divots and pockets directly on a roof. And so we'll turn on the anomaly detection, which happens to be, at this point, a combination of a long short-term memory model and a convolutional neural network. And what you'll notice here is that you get a unprecedented amount of accuracy in terms of what's fully happening on the roof. The status quo in this market, which I'm pretty sure no one in this room knows what the status quo is, but I'll just tell you really quickly, is someone climbs the roof, you take a 10 by 10 measurement of a portion of the roof, and then you extrapolate what the rest of the damage looks like. So what's wrong with that, right? So if I took the measurement from here, it would have vastly overestimated the damage because that portion of the roof and that portion of the roof are actually not that damage. However, if I had taken it from here, I would have underestimated the damage because I would have missed all the damage of, again, this is a standard north to south weather pattern that you see here. So this kind of assessment is more accurate, safer, and it's kind of really enabling that industrial work to happen in a more seamless manner. So I think you guys get the gist of the use cases. Where this is all going in the next few years is what we think of as effectively this creation of digital twins that start to converge physical and cyber assets together, digital assets in a meaningful way. The more that you can create these physics models that can synthetically generate what the future productivity of that asset is, the predictive mean time to failure of that asset is, it's all going to be related to getting the physics around it, the physical manifestation of the dimensionality, as well as additional aggregations, calculations directly into the model. How the underpinnings of all this works is that the photogrammetry pipeline is one of the places that we can get these highly accurate models. We decimate that into a point cloud that generates these little these triangular meshes. Every one of these triangular meshes is now hyper accurate within 3 centimeters of real space, X, Y, and Z. So we have positional accuracy down to a level of detail where when you construct the entire asset, it's going to be physically accurate every time. You want to be able to measure this at any point in time and see the change in time occur, particularly when you look at this kind of data from a time series perspective. So how this is all happening is, first and foremost, the innovation at least what we focused on up front was to build a fully autonomous drone that you don't really need a manual pilot to fly. Like literally, it is built in a way where you punch in the geofence, you punch in the asset area that you want to fly over, you hit the start button, the drone autonomously takes off and collects the sensor-based information in a natural way. When it's collecting that information, it's doing that with a package of sensors, mostly visual sensors, a LiDAR, GPS, and additional accelerometers, gyratometers kind of built into the product. And when the data is actually collected, it's being pushed back into the iPad because we're in these industrial work sites where you don't have full internet connectivity. When the iPad has full internet connectivity, we ship it into a cloud processing layer where we process all that data. So the underpinnings of that today look like this. We have real-time telematics going into our cloud largely to have all the instrumentation of knowing where all of our drones are at any point in time. So we've got several hundred drones that have flown several thousand missions over the last few years. And we have the payload largely moving back to the iPad. The iPad then sends it into our AWS cloud infrastructure where the photogrammetry stitching, the machine learning models that I just showed you a moment ago all start to kick in. And then we expose a full layer of applications by industry. In this case, the applications are around volumetrics, analytics, reporting, inventory management that gets specified on an industry by industry basis. So that's really how we see this kind of market emerge for a more complete application. We don't wake up in the morning and think about building a great drone. We're certainly done that, but it's about being able to really solve for these meaningful use cases inside of industrial work sites. So in closing, I'd say that this is a moment in time where we're starting to see, I don't know if anyone's read anything by JCR Licklider. So if you haven't, I'd probably recommend the paper he wrote in 1960. It's called Man-Machine Symbiosis. And what was really cool about what JCR Licklider wrote, even back in those days, the guy literally wrote the earliest UI, or the theory behind the UI for what a mouse would be, and sort of a few other sort of things even before they were invented. And so Licklider talks about the future work not being about machines kind of replacing us. And again, think about this. This is like things that we talk about today. But he said it in the 60s. He said that the future work is not about machines replacing us. It's about machines augmenting the human potential. And so I think that there are ways, particularly when it comes to this kind of industrial work, we can actually use a new sensor network, artificial intelligence, and really the convergence of these physical and digital assets to really understand not only the meaning of work, but also just how much we can actually streamline all these sort of dangerous conditions and get a better work product, particularly for these industrial use cases. So that's all I had for today, and glad to take a few questions. Oh, and I love being back in New York, so invite me back anytime.
Thank you.
Thank you for a very interesting presentation. I'm curious, again, I know your focus is not the hardware and the analytics are amazing, especially for the verticals. But I'm curious about your thought, especially because Kespry is really the only success in a vertically integrated company that's out there. Are you worried about DJI's drop in cost curve and increase in feature curve and how they, their kind of Apple model where there'll be some of the, a specific company doing analytics sitting on a DJI drone? Does it keep you up at night?
Well, we would like to think of ourselves as the Apple model in relative comparison to the others in the market. It does keep me up at night, and not to be pejorative, it does keep me up at night that there is a cost curve on drones that is continuing to drop, and the industrial nature of what you could do with a drone off the shelf is way better today than it was when we had to build our own drones several years ago. The flip side of it is we're not going to be wed to our own hardware alone, right? Because if you really think about what I described here, our drones are very much effective for some of these industrial use cases, but there might be a moment where a Mavic with autonomy that we might end up providing the autonomous capability set to can fly over a rooftop just as easily as our industrial drone could. And so I see a future, at least for ourselves, being one where there's a mixed fleet of our drones, other people's drones, and more interestingly, you may have seen the announcement this past week where we raised our Series C, and Shell and a few interesting industrial ABB, I didn't want to mention ABB, but yes, ABB as well, all came into the round. But all of their interest is not about the drone per se, it's about the analytical pipeline, it's about the ability for us to process sensor-based data. And so a big part of Kespry's future is as much about the analytics and the data pipelines and the processing layer that it is about the drone itself. As long as we can get more solid sensor-based sources of information, we're just going to be continuously in the business of data processing.
Yeah, my question is that are these drones capable of flying inside the construction site? Like
yeah, so the drone that you saw that we built is mostly, it's completely for outdoor work, right? And so what's been happening in the drone space is there are drones that have now been built for great indoor use cases. And so the combination of things that have been built for indoor use cases as well as just kind of robotic devices in general, like the use case with Shell we're talking about is not just the use of a Kespry drone, it's the use of a Kespry drone with other robotic devices, autonomous robotic devices that are all going to be merged to create these sort of digital twins of physical assets. So we just don't happen to be manufacturing one of those drones ourselves. I know that there's a great company in Europe called Flyability that did an inside focused drone. There's other land-based robotics, rovers, et cetera, that also do great work. In most of the indoor use cases, what's really interesting is LiDAR is actually becoming more and more advanced. So it's all going to be kind of SLAM networks and LiDAR that are driving the topology mapping of indoor space. And there's still, I think, a little bit more sort of weight performance issues on the LiDAR side, just to put in perspective. Today, the best three-dimensional LiDAR you can get in market from a weight standpoint is still about 2.5 pounds. And so for a micro UAV class drone, it just wouldn't fly, literally would not fly with that kind of payload. But if it's a rover, it might work perfectly well. So it's all coming together. This is all very, very interrelated data in a lot of ways.
So while inspection of a construction site, are there any privacy issues with the neighborhood areas?
Privacy? What's private? No. Yeah, no, there is.
Like we are not informing them?
So what we tend to do on the privacy work is there's examples, particularly in the Harvey Irma scenario, where we literally punched in mission plans that were focused on covering multiple properties within a block that happened to be under one carrier, and the drone literally did not fly over properties that were not under that specific carrier that we were flying over at that time. it's public info now, so it was farmers that we do this for. So there's ways to be able to manage the privacy appropriately, particularly with a geofence, to say that when you're on a construction site, you're not having the drone fly over someone else's workspace and intruding not only on privacy, but perhaps even taking imagery and other sensor-based information from that workspace or that private property. And so we've got a lot of that instrumented into even just how we collect data up front in our drones.
Your above ground level calculation is done by LiDAR or based on stereo disparity?
The above ground calculation that you saw in the demo that I gave is fully photogrammetry based. So the idea there is that because I can take a series of angled images, I can actually construct X, Y, and Z properly. And so I have the full volumetric height of how much material I have within that stockpile based on the angled images that I'm stitching together into a 3D orthomosaic. So what ends up happening then is the portion that I cut, right, that I want to calculate, I could literally have drawn any polygon there, right, and said, oh, just show me that portion of it, cut the base plane, and then calculate everything that's above it.
I'm curious as to how the insurance companies have reacted to the notion of automated classification of the dings that you get from hail damage.
It is. I mean, like literally. To repeat the question, it's just how do insurance companies reacted to things like automation of hail and other anomalies on the roof? This is, I kid you not, like a work in progress right now, right? Because you're introducing something that's like sheer magic, right? For the way that kind of work has been done before. So we've been working very closely with the experts that have been in the roofing space that literally do the engineering work to assess the level and extent of damage. Hague Engineering is one of those companies that certifies this kind of work. We've also been working with all the carriers. Some of the carriers have their own algos that they want to be able to bring into the mix. So ultimately, we're not trying to say, hey, is this hail or is this not hail? What we're trying to say is there's an anomaly on a roof and we've properly detected it. And people are now more confident than ever, and particularly after this last round of superstorms where you just could not manually do all that work, they're more confident that they should be using some algorithmic method to support whatever the adjuster is on site, largely, again, as I mentioned, augmenting that human potential, not having the robot do it themselves, nor having the human do it themselves.
Hi.
Right,
Thanks.
you're
Yes.
hiding behind light, so I cannot see you.
So, quick question. My understanding is that FAA regulations require drones to fly within line of sight today. Are you working within that restriction? Do you have use cases where you need to go out of line of sight, and how do you manage those situations?
Yeah. So we've flown, as I mentioned, well over 40,000 missions. So we're absolutely within FAA regulations. So here's the regulation that as it stands today. There's three pieces to it. One you mentioned already, which is staying within line of sight, which is depending on how open the airspace is and what else is in the airspace. You're talking about 2.7 miles on a clear day. So absolutely, you have to have unaided line of sight to the drone when it's flying. You can't even use binoculars. The second piece of the regulation is the drone has to stay below 400 feet of airspace, which we have programmatically built into our software where none of our drones can fly beyond 400 feet, even though technically they could, but we put a limiter on it. And then the third piece is that you have to have a Part 107 pilot's license, which is effectively like taking the written portion of the driver's exam in New York or California. So as long as you have those three pieces in place, you can commercially fly anywhere in the country. Our customers all go through all three of those pieces, including the Part 107 certification before they fly. And one of the things that we're now seeing is, I was actually at the Trump administration, I was at the White House just earlier in the year, and we were brought there to talk about drones and 5G and IoT. And so one of the things that came up was, is there going to be a micro UAV category where some of those restrictions might be eased up? So it's about a year or two away before it is, but right now, we've got the right regulatory framework to do business in North America, and it works perfectly fine.
I got Two questions, actually. What's your business model?
Yeah, so the business model is a subscription-based model. So our model is that we sell a unit of a Kespry drone, including the data pipelines, the analytics, the models, the applications, and the APIs all packaged up as a single subscription. And then as our customers start to use more of the entire product suite, we land more units over time. So our customers go from a single unit subscription to 10s, 20 unit subscriptions within several quarters of landing the initial customer. So in that sense, it's a very traditional SaaS-based business model. It just so happens that in our model, we have hardware and software as a converged system versus pure software. The drone is a subscription. It's part of the subscription. So if the customer chooses to end the contract with Kespry, which rarely happens, if ever, but when it happens, we take the drone back.
All right, on this note, George, thank you so much. It's wonderful. Terrific.